This video is on figuring out average isotopic mass problems. So there are two different ways, but just before we go into it, let's have a review. An isotope. Isotopes are atoms within a same element, so they have the same number of protons, but they have a different number of neutrons, so they have a different mass. Most elements have more than one isotope, and the most abundant isotope is usually the most stable isotope, and that's because it's really the ratio of protons to neutrons that affect the stability within a nucleus. Unstable nuclei will usually shoot out nuclides, those are protons or neutrons or other particles, out of the nucleus until it reaches the most stable proton to neutron ratio that you can have. That's called nuclear decay, which will be actually covered in a different topic later on. Take home, different number of protons, same number of protons, different number of neutrons, makes a different mass, and the most stable one is the most abundant. Because most elements have more than one isotope, the mixture of all of those different isotopes will usually lead to a mass, an average mass that is not whole number, and that's why often on the periodic table, most of the masses that are there will be non-whole number masses. So the first example of a type of problem is where the percent abundances are known. So here's a sample problem. I have 3 isotopes of chlorine with a mass of 35, mass of 36, and chlorine with a mass of 37. And these are their percent abundances that will be given. It's really important to note that all of these percent abundances have to add up to 100% because you have to count for everything within your sample. So 60 plus 22 plus 18 equals 100. Whenever you're given percentages in a math problem, you should always convert to decimals if you're going to do math with it, so arithmetic. So 60% converts to 0.6, 22 to 0.22, and 18 to 0.18. Then I take these decimals and I multiply them by the masses that they correspond to. So 35 times 0.6, 36 times 0.22, and 37 times 0.18. These are the products of those. Then I add it all up, and that will be your average isotopic mass. So again, you take your percents, you change them to a decimal, you multiply the decimals by the corresponding mass, and you add it all up. Then you check for logic. So my isotopes are between a mass of 35 and 37, so my average should be somewhere between 35 and 37. And I have more of chlorine 35, so my mass should be closer to 35 than it should be to 37, and 35.58 is between 35 and 37 and closer to 35. Okay. Second example of a type of problem is where you don't know what the percent abundances are. You have to solve for them. So the problems that you will encounter, there will only have 2 unknown percent abundances. So the example that I give is there are 2 isotopes of silver, Ag, in a sample. Ag with a mass of 107 and Ag with a mass of 109. The average mass of this mixture is 107.87 grams per mole. What are the percent abundances of each isotope of silver? So I don't know the percent abundances, so it'll be X and 100 minus X, because again, the percent abundances should add up to 100, and 100 minus X plus X is equal to 100. I change the percents to decimals, so this becomes X and 1.00 minus X, and then I multiply these to the masses, so 107 times X and 109 times 1.00 minus X. And that should equal the given average isotopic mass, which was given in the problem. I then solve. So 109 times 1.00 minus X plus 107 times X is equal to 107.87. I distribute out the 109. That becomes 109 minus 109X plus 107X. I subtract 107 from both sides, and I combine these like terms right here. And then I move the variable over to this side, and I end up with 2x is equal to 1.13. If you left the x's on this side and left the number on this side, then you'd end up with negative 2x is equal to negative 1.13. You would divide by negative 2 instead, but either way, you're going to end up with a positive number. And it has to be a positive number because percent abundance is a positive number. You can't have a negative percent abundance. So I end up with x is equal to 0.565. That's a decimal, and I have to convert that to a percent. So I multiply it by 100. So my percent abundance for my silver is 56.5%, and then my percent abundance for 109, silver 109, would be 100 minus 56.5, or 43.5%. Then you check for logic. So I have a higher percent abundance for silver 107, so my isotopic ratio, my average isotopic mass, should be closer to 107, and it is. So the given isotopic mass, average isotopic mass, is 107.87. That already gives you an idea that you'll have a greater percent abundance for the isotope of silver 107 rather than silver 109. So I hope that this was helpful for figuring out average isotopic mass problems.